All right, well, welcome to the last day of Math 105. Our plan today, we're going to go over the quiz, go over any homework questions people might have. And then there are a few more things I want to talk about with antiderivatives. And then once we're done with that, we'll kind of talk about what to expect for this final exam, like what kind of key points you need to look for and kind of remind ourselves what's happened over the past few months. Anyway, so with that, let's start by talking about the quiz. In general, it went really well. Really, the biggest issue was just with the third question, or the second part, I should say, of the question number 2. So let me go to a whiteboard. Share my whiteboard screen. And let's just kind of look at these real quick. All right, so for number 1, we were given a function f of x equals x cubed plus 3x squared minus 2. And I wanted to use Newton's method to find the positive root for this function. This actually has more than one root, but it has only one that's positive. And I specifically asked you to go ahead and start with a guess of 1. Okay, so using Newton's method, we need the derivative. So that's nice and easy here. That's just 3x squared plus 6x. And so what we know for Newton's method is that our next best guess is going to equal our current guess minus f of x over f prime. It's always this form, and hopefully you remember where that came from. That came from finding the x-intercept of the tangent line. And so for this one specifically, we're going to have x cubed plus 3x squared minus 2 over 3x squared plus 6x, right? That's what f and f prime are here. All right, so if we start with a guess of 1, you plug in 1 into this formula right here, and what you end up with is 7/9. Right? As a decimal, it's 0.7 repeating. Okay, so there's x2. Now, if you take 7/9 and you plug it into that formula, I'm going to do this as a decimal. We could do it as a fraction. The fractions get big and ugly fast. But as a decimal, 733756661 ... Okay, so it changed again. It didn't change a lot. We went from 0.777 to 0.7337, right? So not a lot of change. So we're starting to settle down, but we need to keep going because I asked you to go to the point where we get 5 decimal points repeating. So if we go to the next one, plug in 0.733756661, blah, 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 you get 0.73205,332. So it's definitely starting to settle down, right? Now we're good to 2 decimal places. If you do one more, you get 0.73205, blah, blah, blah. And now you can see that we're actually good to 5 decimal places. So there is the positive 0 for this function to 5 decimal places. All right, so there's number 1. Any questions on that? Okay, so then for...
Oh, I have a question.
Oh, yeah, go ahead.
Okay, so I got the same answer, but I only needed to do the iteration 3 times. I did it three times on your quiz, but if you count 1, I think I did it 4. But you did it 5 times and you still got the same answer. So, like the way I did it, I kind of just made a chart. Would that be okay, acceptable on the final if I just kept my chart?
Okay.
It's easier to understand. Like I like your idea and I like how you clarified like the proper way to do it, but then like when I made a chart, I think it was easier to like see it. So
Okay.
like I want you
Can
to
I?
know like which
Okay.
which
Can I answer your question? Just go ahead and pause, because then let me answer your question. I'm just laughing because every time I start to talk, you follow up a little bit more. So here's the deal. The reason I went to a fifth one is because when I got to X4, even though you notice that X4 still has the same first 5 decimal places, the thing is, I don't know that that's actually good to 5 decimal places if all I get to is X4.
Okay.
Right? I have no idea, because what's the next one going to be? The next one could be 0.73194, like I don't know. So I went one more time until I got the same starting 5. So in terms of like, when do I first run into this number? Yes, I first run into it at X4. Absolutely. But I don't know that. There's no way for me to know that that actually is good to 5 decimal places until I go to the next one. So does that kind of make sense why I went to X5?
Yeah, it does.
And I think, and I don't know, but I think sometimes when we run into that kind of thing, you already know what the answer is because you've done something like you've graphed it, or you've used some sort of a solver. And so you already know what your target number is. And so if you already knew, oh, it's supposed to be 0.73205, and then you run into this, you go, oh, see, I got it. But that's assuming some information that we don't actually have, right? It's basically assuming you already know the answer. So in general, what you want to do is you want to keep going until you get to the point where that next one looks the same as the previous one. And just writing it as a chart is fine. I mean, that's basically what I did, right? I just wrote it as a chart. But you got to make sure that you go far enough that you know what your answer is.
Okay.
So does that make a little more sense? Or
yeah, because in the text, I had like an old calculus textbook, and then it had the chart, and I was like, oh, that's a good way to do it.
Yeah,
so
totally.
Do my homework.
Yeah, and that's fine when it comes to how you want to organize it in your process. I'm totally cool with you doing it the way that you want to do it. Just make sure that you go far enough that you know you're right.
Okay, thank you.
Yeah, you're welcome. All right. So the next question was just a limit, and it was the limit of e to the 3x minus 1 over the tangent of 2x. And if you plug in 0, e to the 0 is 1, so 1 minus 1 is 0. The tangent of 0 is 0. So since it's 0 over 0, that definitely suggests we want to do Logital's rule. Okay, so we'll do Logital's rule. Still going to have the same limit, but now we differentiate the top and the bottom. So the derivative of the top is going to be 3 e to the 3x. That comes from chain rule. Right? E to the 3x, its derivative is e to 3x, and we multiply by the derivative of the exponent. The minus 1 goes away. And then on the bottom, we're going to get 2 secant squared of 2x. So again, chain rule. Derivative of tangent is secant squared. The derivative of 2x is 2. And now if we plug in 0, we're going to get 3 times e to the 0 over 2 times secant squared of 0. Well, e to the 0 is 1. Secant of 0 is 1. So secant squared is 1 squared. And this ends up being 3 halves. So the limit of that one is 3 halves. Now, most people did just fine on that. It was 2b that was the bigger issue. So let me go ahead and erase over here. Any questions about 2a there before we jump on to b? All right. So for b, we were looking at Oops, I guess I should have erased up there too, huh? 2b. We got the limit as x goes to infinity of 1 plus 1 over x to the x. All right, so if we plug in infinity, we're going to get 1 plus 0, which is 1, raised to the infinity power. And 1 to the infinity is yet another one of the indeterminate forms. So we're going to want to use Logital's rule. But we can't use Logital's rule directly because of the fact that this isn't infinity over infinity or 0 over 0. So what we're going to do is we're going to take a log. Okay, so if I take the natural log, get the natural log of y is equal to the natural log of 1 plus 1 over x to the x. I can bring that x out front. So we get x times the natural log of 1 plus 1 over x. And if you were to plug in at this point, plug in your infinity, you're going to see you get infinity times the natural log of 1. And the natural log of 1 is 0. So it's still indeterminate form, but it's getting a lot closer. And we know what we need to do when we have 0 times infinity. We just need to turn this into a division problem. So I either have to divide by 1 over x or divide by 1 over the natural log of 1 plus 1 over x. Well, I'm going to choose the easier. So I'm going to divide by 1 over x. And so now this gives me 0 over 0. So that is exactly the form we need to do Logital's rule. So let's do it. All right, so on top, I've got the natural log.
Bruce, can I ask quickly why you decided to divide by 1 over x?
Because it's going to be easier than dividing by 1 over natural log. So maybe the actual question is, why did I divide by 1 over x? Not why I chose that. And the reason that I divided by 1 over x is that these are equivalent. Dividing by 1 over x, think about fractions, division. You can flip it and multiply. So that's exactly the same as multiplying by x, right?
Oh,
so,
I see. Okay, sorry. I was just thinking about the 1 over x in the parentheses and I got confused. Gotcha.
Yeah, no, that 1 over x, that's coming from this guy, became 1 over x.
I have a question. Did you expect us to put the? I know it makes it easier to see, but the 1 to infinity, like the form.
No,
of the.
no,
Okay.
I don't care about that.
Thank you.
I just do that to show you guys kind of the progress and why we go to here, because you always need to get to either 0 over 0 or infinity over infinity to do Logital's rule. So that's purely just to let you see what's going on. Okay, so we're going to now have the limit as x goes to infinity of, well, let's differentiate. So with the natural logs, remember the process for those, we're going to get a fraction. On the bottom of that fraction is what's inside of the log. So that's going to be a 1 plus 1 over x. And then on top of that, we need the derivative of what's inside the log. So the 1, of course, goes to 0, and 1 over x, its derivative is negative 1 over x squared. So this fraction is the derivative of the natural log of 1 over 1 plus x. Or sorry, 1 plus 1 over x. All right, now on the bottom, we need the derivative of 1 over x. Well, we already did that derivative actually in the chain rule above, so it's the same, minus 1 over x squared. Okay, so before we take this limit, let's simplify this a little bit. I'm going to multiply everything by a minus x squared. Right? Or if you want to think about it, since we're dividing by this fraction, it's the same as flipping it over and multiplying. And when you do that, you get here. So really just those minus 1 over x squared cancel. So now we put in infinity. 1 over infinity, of course, goes to 0, and this equals 1. But we're not quite done, because what we just found was the limit of this thing, which was natural log of y. So we know the natural log of y equals 1. So if we just convert that to exponential form, that tells us that y is equal to e to the first, or y is equal to e. So that's what we can box. So this limit equals e. All right, so 1 to the infinity can actually be anything, and in this case, it's e. And just a little fun fact for you, that number e, when it was first kind of discovered, it's actually been known for quite some time. It hasn't been called e for very long, but it was known by the ancient Babylonians. They were business folk, and they knew about compound interest. And this is actually how e is defined, believe it or not, is with that limit. But now we can see why that limit equals e. All right, so there's the quiz. So those scores are in, which means the grade book on Canvas is up to date. Everything is in there. The one thing that hasn't been done, and it's because it can't be done on Canvas, is the dropping of your lowest exam score. Right? Remember how if you do all your homework with a score of at least 50%, I drop your lowest exam score. I can't do that individually. It has to be either everybody or nobody. And the problem is not everybody gets to do it. So that hasn't been done. So if you look at your grade on Canvas, if you are eligible for dropping your lowest exam score, your grade is actually a little bit higher. Everything is done on a weighted average. So what you can do is, instead of taking the overall average of your 3 exams and multiplying by, I think it's 40% is what the exams are worth, you can just take your highest 2 and do that. If you are curious, you're like, I'm not really sure what it looks like if I drop my exam, send me an email. I'll be more than happy to reply to you with a what it looks like with your exam score dropped. I don't ever mean for it to be a secret, right? It's just I'm limited by Canvas's ability. Anyway, so your grades are up to date in there. There may just be the couple of homework assignments that you haven't finished yet that can still affect that. But you should have a pretty good idea of what your score is looking like going into the final. All right, so speaking of homework, and I think there are only the 2 homework sets that are still out there. They're due Monday. Again, Monday night at midnight. We'll already have the final exam taken, but I wanted to give you the same due date just to kind of keep things regular. Are there any questions about either of those open homework sets or anything else we want to talk about? All right, so Eric just put in the chat he'd like to look at number 12 from 4.10. Any others? All right, well, then let me go ahead and share the screen and we'll go look at number 12 from 4.10. Side note, always makes me chuckle when you've got a section like 4.10, because of course to a mathematician, isn't this exactly the same as 4.1? So I guess that means that the 10th section and the first section are the same. No? All right, it's too early for that. All right, it's about time. All right, now it's possible that this one covers something that I haven't talked about yet. And if that's the case, I might ask you to hold on a little bit. All right. All right, so this one says a stone is thrown straight up from the edge of a roof, 625 feet above the ground, at a speed of 12 feet per second. Remembering that the acceleration due to gravity is negative 32 feet per second squared, how high is the stone 4 seconds later? At what time does the stone hit the ground? And what is the velocity of the stone when it hits the ground? All right, so horrible word problem here. And this does require a little bit more than we've talked about with antiderivatives, but I think we can kind of, we'll start the discussion here with this one. But basically, if you think about what we're trying to do, like you look at that first question, it says, how high is the stone 4 seconds later? We're basically looking for a function that tells us the height, right? We'd love to have a function that you plug in a time and it gives you a height, gives you a position. But we're not given it. And in fact, all we're told is the acceleration. All right, well, this is where antiderivatives come in. So I'm going to go ahead and switch to a whiteboard. But while I'm doing that, let me ask you guys this. Do you remember how you get acceleration? Like
That's the second derivative of the position function.
Yeah, so if you have your position, you differentiate it once, you get velocity. You differentiate it a second time, you get acceleration, right? So we already saw that if y is the position, then y prime is velocity, and y double prime, that's your acceleration. All right, so we all remember that. Now, what we can do in this case is, since we know acceleration, we want to find position, we got to go the other way. So what does that mean? Well, that means we need to anti-differentiate, right? Because when we're going down this list, these are derivatives. So if we're going to go up this list, these are going to be antiderivatives. So here's actually a very good example of why we would want to do an antiderivative. Because maybe we're told an acceleration and instead we want to find position. For those of you who are going to go into physics, like starting next quarter, by the way, just let me give a little plug. Calculus-based physics, Physics 107 starts in the winter quarter. If you are thinking about going anywhere along the lines of physics, engineering, astronomy, that kind of stuff, take Physics 107. Absolutely take it. Take it next quarter, get into that sequence and start going. All right. So anyway, so for those of you who are going to take that class, you're going to see that this is something you always do, because accelerations we can figure out pretty easily. And once you've got an acceleration, you can actually work your way back to position. Okay, so let's see if we can do this. So we're told that the acceleration is negative 32 feet per second. Now, I'm not going to put the units on there just because they're going to make everything kind of messy. But it's minus 32 feet per second squared is our acceleration. Okay, so that means that our velocity is going to be the antiderivative of acceleration. And remember, we need to put a little differential here. Well, our variable is time. If you recall, when we differentiated to go from position to velocity to acceleration, we were always differentiating with respect to time. So that means when we do our antiderivative, when we go the other way, it still needs to be with respect to time. All right, so far so good?
Yep.
All right, so let's anti-differentiate this. What kind of function gives us a derivative of negative 32? All right, so beautiful. So we're going to get negative 32, because it's a constant multiple. And then when we integrate the dt or anti-differentiate the dt, we get t. So as you put in the chat box, a minus 32x, you're thinking right. We just want to make sure we're using the right variable. It's a minor thing, but let's try to match those variables. So we get minus 32t. Now what else do I need to put here? Do you remember?
Plus 18 because or it's plus c, but it says it's, or I'm sorry, I'm reading a different one, but mine says it's thrown straight up at a speed of 18 feet per second. Would that be included in the velocity function?
Yeah, we are going to need to include that, but let's just start here that we know that we need to allow for a potential adding of something else, right? Because a constant, as we saw when we differentiate that constant that's being added, it just disappears, right? So we always have to put that little plus c on here. So the thing is, we don't know as of right now, we don't know the velocity exactly. We know we're good off to, or up to at least a constant. But the problem is that's not good enough if we want to be able to answer that exact question. So we are going to do exactly what, I think that was you, Tim, right, who was telling me that?
Yeah.
We're gonna do exactly that, which is we know something about the velocity. Let me go back to the problem here, right? So it tells us that the stone is thrown straight up, from 625 feet above the ground at a speed of 12 feet per second. So we actually know something about the speed. We know that at the very beginning, its speed is 12. Okay, well, if we go back to the whiteboard then, here's what I know. I know that when t is 0, v equals 12, right? If t is 0 is at the start, we'll let that be when we decide to start our time, then we know that the speed is actually 12. Well, that's going to make it so that we can actually figure out what that c is, right? So we're going to get 12 is equal to minus 32 times 0 plus c. So c is equal to 12. All right, so then our velocity is given by this. It's minus 32t plus 12. So Tim, you're right. Like this 12, the fact that that was the initial velocity, that's always going to be the case if we're starting with time equals 0 as when we're actually beginning the throwing. This is going to be our initial velocity. So if we had been throwing it upward at, I think you had said 16 feet per second. Okay, this would have been plus 16. Upward at 4 plus 4. If we had thrown it down with velocity, this would have been minus, right? So if instead of throwing it up, I'm throwing it down at a speed of 12 feet per second. This would have been minus 32t minus 12 and so on. All right, so we were actually able to figure out the exact velocity because we knew something about velocity. All right, so there's our velocity. So now let's get our position. And we're going to get our position by doing the exact same thing. I'm going to call it h for height. You can call it whatever you want. But now I need to anti-differentiate velocity. If you come back here, we're on that now second step back up. So just like getting acceleration required doing two derivatives, going from acceleration to position is going to require two anti-derivatives, right? We're going to have to integrate twice. Okay, well, let's see what we get for this one. All right, so we're going to get minus 32. It's constant multiple. When we integrate t, let's use the power rule. So this is t to the first. So we're going to add 1 to the exponent and then divide by that exponent. So we're going to get minus 32 times t squared over 2. And then for the 12, all right, well, the 12 is a constant multiple. And then we're just integrating dt, which gives us another t. So we've got minus 32 times t squared over 2 plus 12 times t. And then again, we have to add on a plus c because we can. There might be something there. So we need to at least allow it. Okay, so h is then minus 16t squared plus 12t plus c. All right, so what we really need to do is figure out c. And we're going to do exactly the same thing that we did before with the velocities. If we go back to actually the problem, we're told a height, right? If you look at this, it says the stone is thrown straight up from the edge of the roof 625 feet above the ground. So that means that at the very beginning, at t equals 0, our height was 625. All right, so we'll just do exactly what we did last time. But now we know that when t is 0, h is 625. All right, well, if you plug in 0 and 625, you get 625 is equal to c, right? Because all that stuff goes away. All right, so here's our formula then. We now know the height of the stone at any given time. So kind of cool that we now have a tool to go backwards. So anytime we had an application where we found derivatives, if we know that derivative, we can go backwards using anti-differentiation. All right, so how are we doing at this point? Kind of seeing the process here and what we're doing. All right, so now we can answer all these different questions, right? Now that we've actually got that position function, if you, let's just go back real quick. Think about what we're going to do to answer these questions. So, so for part A here, right? How high is the stone 4 seconds later? Well, remember that formula we just got. Plug in t equal 4. For part B, at what time does the stone hit the ground? Well, we'll take that equation that we just developed and set it equal to 0 because the height of the ground is 0. For C, what's the velocity of the stone when it hits the ground? Well, remember from part B, we know when it hits the ground. You can take that time and plug it into the velocity formula, and that'll give us the speed when it hits the ground, right? So now we know everything there is to know about this stone. You want to know its velocity ever? No problem. We got a formula for that. You want to know its height ever? No problem. We got a formula for that. And it all came from anti-differentiating that acceleration. So we do this all the time in physics, where you start with an acceleration and you find velocity and position. All right, so how are we feeling about that? Is that feeling pretty good about that, Aries? Yeah. All right, well, let me just, while we're here, talk about a couple things. First of all, you can totally generalize this, right? So instead of having a specific acceleration, right? So we're saying the gravity is minus 32 feet per second, pulling it down. You could allow for anything. And so if we just called that A, let's just kind of generalize this, then V is going to be the integral of A, which is going to be AT plus C. And that C, remember that C over here came from the 12. That was our initial velocity. And so what we could do is actually just be really generic and write that as V equals AT plus V naught. And that V naught, all that is, let me actually write it over here. V naught, this is your initial velocity. Okay, so that's just all I mean by V naught. All right, well then, if we wanted the position, remember H then is the integral of that, which is going to be 1/2 AT squared plus V naught T plus C. But that plus C, like we saw in this problem, was the initial height. So I'm going to rewrite this as 1/2 AT squared plus V naught T plus H naught, where again, H naught is the initial height. And check this out. So if you see this formula right here, you have now done every single constant acceleration problem. I don't know if you realize the power of that, but if that acceleration is not 32, but whatever, yeah, you just plug it into that formula, get your initial velocity, your initial position, and you're done. So to a scientist, so remember I kind of live in two worlds. I'm a mathematician / scientist, I guess. I don't know. Not that I actually do much science anymore, but to a science-minded person, this is freaking awesome, man. We now have a formula that always works when you have constant acceleration. And we only had to do the math one time. And so you'll see a lot of this when you take physics, specifically the calculus-based physics, like the majors physics, and integration, anti-differentiation is going to be one of your main tools, because we know accelerations. And once you have accelerations, you can backtrack and find position. All right, so this is a little bit beyond what we had talked about last time, and something I definitely wanted to talk about today, which is what we call initial value problems. So once we're done with homework stuff, I'll hop to the whiteboard and we'll talk a little bit about what we just did right here, but kind of more formalize it and look at it how we do it in general. All right, but good question, Eris. Thanks for asking about this one. Hopefully now you're good to finish off yours. Other homework questions? Anything else we want to talk about? Okay, so I'm not hearing any, I'm not seeing any. So I'm going to go ahead and jump up to the whiteboard and we'll talk just a little bit more about anti-differentiation and then review. All right, so what we just did when we actually found the values for those C's, we call these initial value problems. And with initial value problems, basically what we know is something about the function. And I'm going to put here beyond just the derivative. Sorry, I'm totally in the glare. Let me move this down here. Okay, so I'm writing what I just wrote here, right? Is I said that we know something about the function beyond just the derivative. Because we already know the derivative. We're assuming that we know the derivative, because otherwise we're not anti-differentiating. So we already know about the derivative. But with an initial value problem, we know something more. So think about this problem that we just did, right? We didn't know just the derivative. I mean, I guess we knew the second derivative, but same story. But we knew something about the function itself, right? Like we knew that velocity. We were tossing it up at 12 feet per second. We also knew the initial position. We were starting up here at 625 feet. So we had some more information than just the rate of change, than just the derivative. And so those are what we call initial value problems. And what's good about these is these let you find the C. So I'm going to put here, they let you determine what that plus C is. So a little bit more information allows us to find a little bit more. In fact, it lets us get the very specific function, right? Because when we just did the antiderivatives before, we knew we were good with just being off by that constant that's being added, but that's fairly significant, right? Like think about what that does graphically. When you add a number to a function, it shifts it up and down, right? The initial value problem, if we got a little bit more information, you can think of it as we know a point that graph goes through. So what we're going to do is we're going to shift this function up and down until now it's going through the point I wanted. All right, and so all of a sudden we're locked into an exact function, not just well, it looks kind of like this, we're not exactly sure which one, right? It brings us to the exact function. All right, well, I've already kind of shown you now how to deal with these with that homework problem, but this is what you're going to kind of see when you run into one of these. So for example, let's say we're told that we know that y prime is equal to cosine of x minus x cubed plus 2. But we also know that y of 0 equals 4. Find y. Okay, so here's an initial value problem. So it's an initial value problem because we're given a derivative And we're also given more information about the function. We're told that at 0, this function is equal to 4. All right, so let's see if we can actually solve this. So without that y of 0 equals 4, if I just said, hey, y prime is equal to cosine of x minus x cubed plus 2, we know what we need to do. We're going to integrate this thing. So we're going to integrate cosine of x minus x cubed plus 2. And our derivative, we're differentiating with respect to x. So we have to integrate with respect to x. All right, so let's see what we get. So the integral of cosine, the antiderivative of cosine is sine, because sine is the function whose derivative is cosine. Minus x cubed, well, that's power rule. We're going to add 1 to the exponent, and then we're going to divide by that amount. We're going to get minus x to the 4th over 4. The 2, well, that's going to give us a 2x. And then, of course, there's the plus c. So we always put the plus c at the end. All right, so this is where we would get without the initial value. But now let's use the initial value. Let's take this 0, 4. Let's put it in here. So I know that when I plug in 0, this has to equal 4. All right, so this is the way just to think about it. Just whatever's in here, we plug that in for our x, and then we just set it equal to whatever the y value is. All right, well, sine of 0 is 0. 0 to the 4th is 0. 2 times 0 is 0. So that leaves us just c equals 4. And so we now have our function. Y is equal to sine of x minus x to the 4th over 4 plus 2x plus 4. So that is the function whose derivative is cosine x minus x cubed plus 2 that also passes through the point 0, 4. So it's one extra step. It's barely an extra step. It's an algebra step, right? Let's just plug in those numbers and see what we get. All right, so a couple things about this though. First of all, it's called an initial value problem because it primarily shows up when we know something about the function at the start. And in an applied setting, the start can be whatever you choose to be the start. But think about that problem that Era's asked about on the homework, the tossing the stone up into the air. We knew initially its velocity, and we knew initially what its position was, right? So that's why it's called an initial value problem. But it doesn't have to be that way. It doesn't have to be initial. It could be, go back to that problem with the rock. It could have been, I didn't tell you how fast I threw it up at the beginning, but I said after 1 second, it has a velocity of whatever. That's still considered an initial value problem, even though we don't have an initial value. But it's still enough information for us to solve it, right? Or just like here, I told you y of 0 equals 4. I could have just as easily said y of 1 equals 6. Okay, well, the only thing that would have changed is instead of plugging in 0, I'd have plugged in 1, and I would have set it equal to 6. And then I solve for c, right? So you can still find that c even if it's not an initial value, if it's not at time 0, at position 0, at whatever 0. You just need to have some information. Okay, so that's the first thing. Don't let initial value make you think you have to know exactly what's going on at the start. You just need to know something. The other thing that I want to make sure you realize, because this hasn't happened yet, is that you may have spotted a pattern here, and I want to warn you if you did see that pattern. Like Notice what the C value was in this case. The C value was 4, which happened to be our initial value. If you go back and you look at the velocity one, the C was the velocity at the start. And then for the position, the C was the position at the start. It doesn't always work that way. Okay. The C is not always what that number happens to be. So you got to kind of be careful with that. Let me show you what I mean. So here's another easy one. Let's go with y prime is equal to e to the x minus sine of x. And I'll give you an initial condition of y of 0 equals -2. Okay, so similar idea. So think about what we're going to do. We're going to start by integrating the e to the x minus sine of x. All right, so integrating e to the x gives us e to the x. Remember, e to the x is your best friend, because whether you differentiate or anti-differentiate, you always get e to the x. Okay, so that's e to the x. The minus sine of x gives us cosine of x, because the derivative of cosine is minus sine. And then, of course, we have a plus c. All right, so to find the c, we're going to plug in 0 and set it equal to -2. So we're going to get e to the 0 plus cosine of 0 plus c equals -2. All right, well, e to the 0 is 1. Cosine of 0 is 1. So we get 2 plus c equals -2, or c equals -4. So the function then that solves this initial value problem is y equals e to the x plus cosine of x -4. And notice how with this one, the number that we're adding on at the end, and I know you see a subtraction, but remember subtraction is adding, but the number that we're adding on at the end is not -2. Right? Those are not equal. And that's just because of the structure of the function. So just be careful, be aware of that. Don't just go, oh, cool, I'm going to plug in whatever that value is in for c and I'll be done. No, don't do that, because it doesn't always work. Sometimes it does, right? Example over there totally worked that way. That's fine, but it doesn't always. So just plug in the number and you'll see what you get. All right, so initial value problem just is, yeah, we're figuring out what that c is that we find when we anti-differentiate. All right, so hopefully you're feeling a little bit better about this, and you're just seeing that anti-derivatives are derivatives just going backwards. We're starting with the answer, and we're trying to come up with the question. Okay, so now you guys are ready for one of my favorite jokes. It's a math joke. It's one of my favorite math jokes. By far, my favorite math joke is, I think I've told you this one, right? What did 0 say to 8? Nice belt. And that is my favorite math joke. But here's my next favorite one. What do you get when you integrate 1 over cabin d cabin? Okay, well, I'll help you figure out the punchline here. Think about what I just said. I want to integrate 1 over cabin d cabin. So here's our integral. That's 1 over cabin.
Oh no.
D cabin. All right, I think somebody sees what's going on here. Was that you, Tim?
Yeah.
Do you see what the answer is?
Is it log cabin?
Okay, close, but not quite. All right, so most people go, oh, it's a log cabin. Not quite. It's a natural log cabin.
Aren't all logs natural versus what, a synthetic log cabin?
I don't know. It could be a common log cabin. But actually, that's not even the punchline. Because what do you get when you integrate 1 over cabin d cabin? You get a houseboat. Because you forgot it's to add the C.
Oh my God.
Get it? C. Okay, it's a terribly bad joke. But yeah, so what do you get when you integrate 1 over cabin d cabin? You get a houseboat. Don't forget the C. It's like a total blend of math / dad jokes. So anyway, I apologize, but I had to. I don't actually apologize. All right, so I think that's a very fitting way to end Math 105 is with one of the worst dad math jokes that there happens to be. But there you go. All right, so we are done now with the new content of Math 105. So let's spend the remaining, what we got, like half hour, something like that. Let's talk a little bit about this final that's coming up, things that I expect you to know, and what you should be ready for. Okay, so first things first, for the final exam, it is Monday morning, so we get to just knock this out at the very, very start. It's at a slightly different time for finals week. It's actually starting at 8 o'clock instead of 8:30. Okay, so the exam Monday morning. It's going to be available at 8 a.m. Okay, so it's actually going to be done the exact same way that all the other exams are done. Right? You're going to go into Canvas. When you click on it, you can pull up the file and start working on it. But it's going to be available at 8 a.m. All right, it needs to be uploaded by 10:30. So I'm giving you the same amount of time. It's the same, it's 2 hours for the exam, and then the extra 30 minutes to deal with whatever kind of technological issues might be happening with uploading. I know a lot of you spill over into that time to keep working. Just make sure you get it in by 10:30. The other thing you need to know is that for finals week, I have a short turnaround time, a shorter turnaround time. So it really needs to get done by then. Okay, so it's slightly different time. Now, in terms of the structure, it's going to look exactly the same as the other exams. It's going to feel very similar, okay? But just some things to know about it. It is comprehensive. Which means anything is fair game from the entire quarter. So we'll talk about some of the things that we did to remind ourselves. We'll remind ourselves what we talked about back in the day. But it is comprehensive. But what I want you to realize is that it is less detail. So it's not as detailed as the midterms. So what I mean by that is I'm looking for more big picture. What are the big ideas from these? Because if I went into as much detail as I did on every other exam, this exam would be like 3 times longer, right? So obviously I'm not going to do that. I'm going to hit just big ideas. All right, so it's less detailed. So I'm looking at bigger ideas. And applications. So basically, what I'm looking for on the final, and I think sometimes students forget the whole idea of exams. The idea of an exam isn't to torture you. It probably feels that way, but it isn't to torture you. It's really for me to see, what have you learned? And so what I want to see is, now that we've gone through this calculus, have you learned how to do the major stuff? And can you use it? Because there's a reason we do calculus. It's not just for the hell of it, right? We do it because we want to be able to apply it to things. So that's kind of what I'm going to be looking at. All right, so along those lines, what are those big ideas? And what are the applications? What are the things that you're going to kind of need to know? All right, well, let's just kind of go back in time. So the very first thing that we talked about after our little algebra review, I don't count the chapter 1 stuff. The chapter 1 stuff, by the way, is not on the final specifically. You're going to need to do it, right? You need to know the rules of logs. You need to know how to find equations of lines and stuff like that. But I'm not going to specifically ask questions on that. But the first thing that we did in calculus is we talked about limits. All right, so let's think back to limits, and what are the things that you should know about them? All right, so first and foremost, you should be able to evaluate them. Expect that on the exam. Hold on, I'll tell you that right now. There are going to be questions on, there's going to be at least one question where it's like, evaluate this limit. So we have a bunch of different ways that we can do that. Not going to make a whole big list of it, but be sure that you know how to evaluate them. The one thing that I'm going to put as a subcategory of this is Logital's rule. Logital's rule is your friend, and you now know it, which means if you ever are working on a limit and you run into a form where Logital's rule could apply, do it, use it. It's a lot faster than rationalizing. It's a lot faster than factoring. It's a lot faster than lots of the algebra things that we had to do before, right? Use Logital's rule, feel free, okay? So definitely know how to evaluate them. And the other thing that's kind of important is know what they mean. Right? So think about what a limit is. A limit is, we're interested in what's going on with a function as we approach a value, not when we're at that value, but as we get close. Okay, so basically, if I ask you anything on the exam about limits, it's really going to be evaluate them or maybe describe what's going on with them. So there were other things, obviously, know how to visualize them on a graph, right? Know how to approximate them with plugging in numbers. Like I think that stuff is probably so second nature now that you don't even think about it. And that kind of gets at what they are. The one thing I will tell you, you may remember that in limits, we also talked about epsilon and delta. You do not need to know that for the final. I will not put anything on there with epsilon and delta. Okay, so don't stress about that. Yeah, just don't stress about that. All right, so after limits, we talked a little bit about some other things like continuity, right, and stuff like that. But again, I think you probably have a pretty good understanding of continuity. But the next big thing that we talked about were derivatives. So things you should know about derivatives. Know the definition. And when I say definition, I don't mean it's the rate of change, although it is. The derivative is the rate of change. It is the slope of the secant line or tangent line. What I mean here by the definition of the derivative is the limit definition. So there were those two forms. The first one was the limit as h goes to 0 of f of x plus h minus f of x over h. And the other was the limit as x goes to c of f of x minus f of c over x minus c. So those were the definitions, and they really got at the same idea. The top, both of them are slopes. Those are slopes of secant lines, but they're turned into tangent lines by taking the limits. The first one is saying h is the gap between the points. So we're making that gap go to 0. The second one is saying that those 2 points come together. Right, they're equivalent idea. All right, so know the definition of the derivative, because I am going to ask you one of these. I'm going to give you a function, and I'm going to say use the limit definition of the derivative to find the derivative. And if you just use the shortcuts, you're not going to earn any points, right? Like if I said, okay, here's a function e to the x, use the limit definition to find its derivative, and all you write is derivative equals e to the x, no points, because you're not using the limit definition. All right, but you definitely want to practice those, because I am going to ask you to evaluate the limit of a function, or find the derivative function using the limit. Okay, so we have the definition. Other thing you should be able to do is to do them. And under the do them are all the different rules, right? Product rule, quotient rule, chain rule, yada, 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 right? This is a huge list. Actually, I'll even make more. Let's see. There was the inverses, implicit differentiation, logarithmic differentiation, I feel like I'm missing something, but I also feel like I'm not. Yeah, whatever. So this was a huge portion of the class, right? I mean, basically an entire chapter was done on how do we do derivatives, right? So make sure you're good with finding derivatives. I put implicit on here specifically, know how to do implicit differentiation, because there will definitely be something on there where you have to use implicit differentiation to find a derivative. Yeah. So I'd say that those are the big things to get from derivatives, is what they are and how you do them, right? But that's easy to say. It's just those 2 things, because there's a lot that's in there. All right, and so then the last big chunk is applications. So let's think about all the different applications we've seen of derivatives. All right, so let's see, we did tangent lines. So we can find the equations of tangent lines. I'm going to write these pretty much in chronological order that we ran into them, at least as far as I can remember. So we did tangent lines, we did related rates. We did extrema. We did concavity. Maybe I can just combine those into graphing, because that includes some other stuff. We did optimization. We did error propagation. We did Newton's method. I guess I'll put antiderivatives here, even though they kind of fit under the derivative list as well. Did I forget anything? Oh, yeah, let me put on here linear approximation. Which is kind of under the tangent lines, but also separate, right? And so the linear approximation, what I mean by that is the whole like, let's calculate the square root of 5 using the square root of 4 as a point that we know about, and then the tangent line and our little delta y and delta x business. All right, so man, that's a big list. We've done so many things with derivatives. But that should kind of make you feel good. It's that double-edged sword, right? Because when it comes to the exams, well, that's a lot of stuff that you need to be able to do. However, it shows you that we didn't do all this derivative stuff for no reason, right? This is definitely one of the things I like about calculus, is that you see the use of it right away. You start seeing why we care about this and what it matters for very quickly, right? And I mean, there's a big list of things that we've talked about. So definitely know how to do all of these, because I will tell you on the final exam, there's going to be a related rates question. Remember what you need to do to figure out that it's a related rate. Look for the words rate. If you're asked for a rate of change, how quickly is something happening? That kind of keys you in that it's a related rate. So I'm going to ask you a related rates question. It's basically get your equation and then do implicit differentiation, right? Know how to find extrema and concavity and all that, because I'll do kind of like on the, what's it, the last exam where I gave you the function and I said, find where it's increasing and decreasing, where it's concave up, concave down, find inflection points. Expect one of those, right? I'll give you a function and just say, hey, tell me what calculus tells you about all of this. And just like that one last time, I am going to expect that your calculus shows it, right? If you just start telling me, oh, it's increasing from here to here because you drew the graph of it on the calculator, not going to fly. You need to justify it with calculus, okay? So expect one of those. Optimization. Yep, you better believe I'm going to give you a problem where I ask you to optimize, but those are pretty easy to figure out as well, right? Look for the keywords: biggest, smallest, best, least, right? And with those, same thing, get an equation. If you need to use a constraint to get it all in terms of one variable, but then differentiate, find extrema, do your thing. Know how to do error propagation, which is, again, it's just differentiate, just put the pieces in where they go. Those are also pretty clear, right? You know when you're doing one of those because it'll say, you know, this measurement is done plus or minus so much, or with an error of, or whatever. Newton's method, I think, is pretty self-explanatory. Those are the kind of questions that I will specifically say, use Newton's method to, right? Antiderivatives, again, it's going to be pretty clear when you see an integral symbol and all that. And the linear approximations, look for it if I say use, you know, derivatives to approximate the value of square root of 5 or something like that. It should be pretty clear when you need to do that. So be able to recognize those kinds of problems, and then be able to do them. Whew. All right, so I mean, that's pretty much this quarter in a nutshell. There were some other things along the way, right? Like we had the intermediate value theorem, and extreme value theorem, and the mean value theorem, and Rolle's theorem, and you know, stuff like that. But in terms of those things, those aren't the bigger ideas. We used them, definitely used them along the way, but they weren't the bigger ideas. So I'm not going to really key in on that stuff. All right, so now that you've seen that, what do we want to talk about? What are you nervous about? What can I help clear up at this point? And if there isn't anything at this point, we can go ahead and call it for the day. I don't have a problem with that.
Can you do like graphing functions using calculus?
Okay.
It's still like fuzzy for me.
All right. We can definitely bang out one of those. All right. I'll just tell you that if I just make it up, it might get, the numbers may not be super nice, but at least we'll talk about the process. So, all right. So that's a good question, Tim. Thanks for that one. Let's do this. Let's just take a function and let's kind of go through the process of drawing the graph of it using calculus. So we'll go with f of x is 2x cubed minus 3x squared plus 1. And let's see if we can get a decent graph of it. We'll look for increasing, decreasing. We'll look for concave up, concave down. Along the way, we'll find extrema, inflection points, put that all together to try to get a decent graph. All right, so let's get the derivative, and let's get the second derivative, because we're going to want both of those. So this is going to be 6x squared minus 6x plus. And then the second derivative is 12x minus 6. So if I'm going to do one of these where I have to draw the graph of it, I immediately just go, let's take a derivative, let's take a second derivative, and go from there. All right, and Ollie, I saw your message in the chat. We'll get to that after this one. All right, so let's start with what the derivative tells us. Okay, so let's look at f prime of x equals 6x squared minus 6x. So we're going to use this to determine increasing and decreasing and extrema. So what we want to do is first look at where is this equal to 0 and where is it undefined. We want to find critical points. So this one I can factor. I get 6x times x minus 1. And so I get two critical points, x equals 0 and x equals 1. So those are possible places where I have extrema. All right, so here's what I'm going to do. I'm going to take the real number line and I'm going to cut it at 0 and 1. And I'm going to look at what is the sign of this derivative, positive or negative, in these different places. All right, so for example, plug in a number bigger than 1. Pick your favorite number bigger than 1. I'm going to plug in 10. So if I were to plug in 10, I would get 600 minus 60, which is 540. Now, the 540 doesn't really matter, but the fact that it's positive 540 tells me that the derivative is positive over here. And so positive derivative, that tells me that my function is increasing. So when I'm to the right of 1, my function's increasing. Okay, so let's do the same thing for the other intervals. Plug in your favorite number less than 0. I'm going to plug in -10. That's going to give me, again, 600 plus 60. So I get 660. It's a positive number. So again, f prime of x is greater than 0. So I know that it's increasing over there. So then lastly, choose something between 0 and 1. And you're going to see that the derivative is negative, which means our function is decreasing. All right, so our function goes from increasing to decreasing back to increasing. So this also tells me about extrema. I know that there's going to be a max at the point 0, 1. Right? When x is equal to 0, I'm at a maximum because I was going up and then I'm coming back down. The 1 I get from plugging 0 into the original function. There's also going to be a local min at 1, 0. So the 1, again, x equals 1 is going to be a minimum because I'm going down and then I'm going back up. And then the 0 came from plugging the 1 into the original function. All right, so that's what the derivative tells me. I now know everything about this thing going up and down, including extreme. All right, so how are we doing at this point? So far, so good?
Yep.
Yep. Okay, so now let's go to the second derivative. So the second derivative, we'll do exactly the same thing. We look where that's equal to 0 or undefined. It's never undefined, but it is equal to 0 at 1/2. So 1/2 is the only place where our second derivative can change from positive to negative. So let's see. And we'll do the same thing. We'll take a number bigger than 1/2 and a number smaller than 1/2, and we'll just test them. So a number bigger than 1/2 would be like 1. I plug 1 in, I get 12 minus 6, which is 6. So I'm told that my second derivative here is greater than 0, which means it's going to be concave up. So over there, it's going to fit on a smile or a cup. If I plug in a number less than 1/2, like 0, I get that this derivative is less than 0. So it's concave down. All right. So however this is going to be concave down and then go to concave up. So that means that there is an inflection point. There's an inflection point when x is equal to 1/2. Let me see if I can figure out what that is. 1/8 times 2 is 1/4. Minus 3/4 is minus 1/2. Plus a 1 is 1/2. I'm pretty sure it's 1/2, 1/2. And again, I just found that y coordinate by plugging the x in. All right, so that's what the second derivative tells me. It tells me the curving, like the curvatureness of this. All right, so let's put this all together. Draw a graph of this thing. All right, so let's start with points I know. I've got a maximum at 0, 1. There's a maximum at 0, 1. I've got a minimum at 1, 0. I have an inflection point at 1/2, 1/2. If I wanted to be really good about this, I would try to find other intercepts and a couple other points, but I'm just going to put together what I know. And I'm going to start with the concavity. I know it has to be concave up once I'm past 1/2. So that means that it has to fit on a smile. And I know that it's going down and then coming up because that was a minimum point. On the left of 1/2, it has to be concave down. So it has to fit on a frown. Again, going through this point is a maximum. So it's going to do something like that. Now, where this actually crosses the x-axis is what I'm saying. I don't really know. I could get there if I did some algebra on that original function. But the shape of 2x cubed minus 3x squared plus 1 looks something like this. And you can see that it matches all the information. We're increasing to 0, decreasing to 1, and then increasing again. Okay, first derivative. Second derivative, concave down until 1/2. And then at 1/2, it becomes concave up. So punch this into your calculator, your graphing calculator or Desmos or something, and you're going to see it looks a hell of a lot like that. All right, so is that cool, Tim? Is that kind of what you were looking for?
Yeah, and then, I mean, oblique asymptotes are also a bit annoying for those, but that's kind of a separate thing.
Yeah, and those only show up in certain forms, right? Like when it comes to what you want to do when you're trying to draw the graphs, you always want to do derivative and second derivative, right? That's an always thing, no matter what the function is. But then you're right, there are other things like the oblique asymptotes. Those only occur when you've got a rational function, right? A fraction, where the top is degree 1 more than the bottom. But you're right, like in that situation, that needs to trigger a, oh yeah, let's find the oblique by doing long division. Same thing with like vertical asymptotes. Vertical asymptotes only ever occur when you have fractions. So when you have a fraction, you got to look for that. You got to look for division by 0. So there are obviously some other forms, some other things that you do from time to time, but all of them, no matter what, require differentiation and using the first and second derivatives. All right, cool. But that's a good question because this actually does have in it a lot of stuff. It's a pretty good review question. All right, so while I was doing that, Alia put in there in the chat box that she'd like to see a logarithmic differentiation problem. So let me do one of those. All right, so logarithmic differentiation is one of those things that can make your differentiation a lot easier. So it's an optional thing in many cases, but in some cases it's necessary. Okay, so I'm going to show you actually one of each. We'll start with this is one where you have to use log differentiation. And then I'll show you another one where you don't have to use it, but it can make the differentiation way faster. All right, so let's start with a you have to use it. So here is a function that I want to differentiate. Let's go with f of x equals, let's go with cosine of x raised to the square root of x. So don't ask me where you'd ever run into this function in real life, because you probably wouldn't. But let's just say that this is what we're going to try to differentiate. Right? So we want f prime equals. All right, so we think about our different rules. This isn't chain rule. This isn't product rule. It's not quotient rule. There's a power, but the problem is this isn't a power rule problem, because this is a variable exponent, and it's not an exponential thing because it's got a variable base. So in this case, we do need log differentiation. So what I'm going to do is I'm going to rewrite this real quick as y equals cosine of x to the square root of x. And I'm going to take a natural log of both sides. So I'm going to get the natural log of y is equal to the natural log of cosine of x to the square root of x. Now, what that allows me to do is bring that square root of x out as a multiple. Right, powers in logs come out as multiples. And now this I can differentiate. Because on the right-hand side, now I've got product rule. All right, so let's differentiate. We'll do d dx. All right, so on the left, this one's going to give us y prime over y. So we're doing implicit differentiation. So the natural log, the trick for natural logs for the derivatives, it's fast. Put what's inside the natural log on the bottom and put the derivative of what's inside on the top. Okay, so that y went on the bottom and its derivative y prime went on top. Now on the other side, we got to use the product rule. So we differentiate the square root of x. That's 1/2 x to the minus 1/2 times the natural log of cosine of x. And we're going to add to that the square root of x times the derivative of natural log of cosine. Okay, well, let's do it fast again. It's a fraction. The bottom is the cosine, and the top, it's the derivative of cosine, which is minus sine. Okay, so to solve for y prime, we got to multiply by y to both sides. So we're going to get y times natural log of the cosine of x over 2 root x. I just don't like the negative exponent. And then over here, we're going to get minus root x times tangent of x. Again, I just feel like making sine over cosine a tangent. So there's one last step. Do you remember what the last step to do here is?
Plug in cosine x to square root x for y?
Yep, exactly. We need to replace that y. But we know what y is. It was the original function. So here's our derivative then. Our derivative is going to be cosine of x to the root x times natural log of the cosine of x over 2 root x minus root x times tangent of x. So that's a pretty ugly looking derivative, no doubt. But we were able to get it. And this is where we needed to use logarithmic differentiation. All right, so really the only thing that we've seen that requires log differentiation is when you have a function of x being raised to another function of x. That's going to make you do implicit differentiation. Or sorry, logarithmic differentiation. But now let me show you an example of where this can actually speed up the process.
Sorry, Bruce, what did you do in that very last step there? You replaced y with the original f of x, is that right?
Yeah, so remember at the very start up here, I had y equals cosine of x to the root x. And I put that in there for the y. So if you look at this piece that's in black and compared to the piece that was in purple, everything in the brackets is the same. And I just out front, I put the cosine of x to the root x.
So because you took the natural log of both sides at the beginning, you don't have to like undo that somehow, right?
Nope. No, because the natural log went away when I differentiated. Had there
Okay.
still been some sort of a natural log of y prime or something like that, then I would have had to undo it. But those natural logs went away when I differentiated. So they're gone, right? I don't have to worry about it anymore.
Okay, cool.
All right, so let me just real quick show you one where log differentiation can be useful. You don't have to do it, but it could definitely speed up the process. So similar vein, we're going to have y equals, let's go with 3x to the 5th minus 4x cubed to the 10th times the sine of 3x plus 1 divided by the cube root of 4x to the 5th minus 2x plus 1. Okay, and I just say find y prime. So like I said, we don't actually have to do anything other than just dive in. But notice that what it would take is quotient rule, because I've got division. In the process of doing the quotient rule, I'm going to need product rule, because I've got a times on top. And then also in the quotient and product rules here, I'm going to have to do chain rule, because I've got something to the 10th and blah, 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 right? Okay, so we could just dive right in. Or we can take a natural log of both sides. If we do that, I can now expand this out. The one on the right, this is going to be 10 times the natural log of 3x to the 5th minus 4x cubed plus the natural log of the sine of 3x plus 1 minus 1/3 the natural log of 4x to the 5th minus 2x plus 1. So I'm using the rules of logs. The things on top have positive logs. Things on the bottom have negative logs. And then any powers I brought out front as multiples. Now let's do implicit differentiation. So we'll go ahead and differentiate both sides. So the natural log of y becomes y prime over y, just like before. On the other side, well, I've got a 10 constant multiple. This natural log, its derivative, again, remember the quick way, is put what's inside on the bottom, and on top gets the derivative. So 15x to the 4th minus 12x squared. Go to the next piece. Natural log of sine of 3x plus 1. So on the bottom goes sine of 3x plus 1. On top goes its derivative, which is 3 cosine 3x plus 1. And then the last piece, minus 1/3 on the bottom, 4x to the 5th minus 2x plus 1. And on top, its derivative, which is 20x to the 4th minus 2. So the derivatives were fast in this form. Differentiating logs is fast, easy once you see the pattern. So now to get y prime, I got to multiply by y. So here's what y prime is going to look like. It's going to be the original y and then that original y gets multiplied to all of this stuff. Oh. I swear it took longer to write it than to actually differentiate it. Now, looking at that, I know is like sad face, right? But there's the derivative. And notice that we didn't have to do product rule. We didn't have to do quotient rule. I did chain rule one time, really. But for the most part, the derivatives were way easier. So logarithmic differentiation is really useful when you've got something gnarly to differentiate that's made out of multiplications and divisions and powers. Because those are the things that logarithms simplify. Anyway, so an example of one where logarithmic differentiation could have been useful, but not necessary. All right. Well, it looks like we're out of time. So I'm going to go ahead and end it here, but I just want to tell you all it's been fun. Hopefully you've had a decent time here learning calculus. And for those of you that are going to be continuing on at LTCC, get ready to see more of this in Math 106 because I'll be the one teaching it, same time, same kind of setup. So for those that will be back, I look forward to seeing you guys in January. And other than that, good luck on your exam, on your final on Monday morning. I am going to be around, so you can send me emails and stuff this weekend. Just realize that on the weekend, I don't always get back to them really quick, but I will do my best to help you out if anything pops up. All right. So with that, good luck, and I will see you all whenever I see you.
Thanks, Bruce. Have a